Today, welcome on behalf of the Center for Crisis Studies and Mitigation at the University of Manchester. My name is Pansi Vanasing. I'm a research associate at the center and the organizer of this series. The purpose of the Center for Crisis Studies and Mitigation is to bring together different researchers across the university working on natural hazards and their impacts on society. First of all, I'd like to thank Professor David Schultz, the principal investigator and lead of our center, for supporting the series. As you can see on the screen, we have a number of great speakers coming up in the next few weeks, and stay tuned for this space because the series will continue into the autumn indefinitely. The format of today's talk will be as follows. During the seminar, you can enter questions into the chat box. We'll do our best to answer all of them at the end during Q&A. For now, let me introduce our speaker today. Very excited to have Dr. Bethan Davies, Senior Lecturer in Physical Geography at Royal Holloway University of London. Her interdisciplinary research advances our understanding of how ice masses behave in different climatic regimes and environments. She's conducted research in Antarctica and Patagonia, Britain, with global glacier on global glacier recession through remote sensing, and she's been awarded a SCAR fellowship to Victoria University of Wellington in 2013. Bethan runs a wonderful website for science communication, which targets glaciers and climate change. We'll put it into the chat box. For those of you on YouTube, it is www.antarcticglaciers.org, and she'll talk a little bit more about that. So without further ado, let me welcome Dr. Bethan Davies to talk today about global glacier loss and the climate change crisis, with evidence from Patagonia and the last glacial maximum.
Okay, thank you very much. Thank you for the invitation to give a seminar. So I'm going to be talking about some of our work in Patagonia, the Patagonian Ice Sheet from 35,000 years ago to the present day. This was published just recently in Earth Science Reviews, and it's freely available. It's open access paper, and it was a really big team of authors that helped to deliver this project. So people like Chris Darville, Has, Jake, Julian, Derek. I can't read them all, but there was a big list of authors who really drove this project and really contributed to the production of it. So thank you to all these collaborators. And we had funding from a wide number of institutions and organizations for this project. I'll start by just asking some questions about why we might be interested in the Patagonian Ice Sheet, and why looking at the last glacial maximum 35,000 years ago is of interest. We currently have about 2 large ice sheets in the world. There's the Antarctic Ice Sheet, which has about 58 meters sea level equivalent. That means that if all the ice in Antarctica melted, global sea levels would be 58 meters higher. So that's just a way of thinking about the volume of ice when we say sea level equivalent. So Antarctica, this continent covered by ice, sea level equivalent about 58 meters. And then we have the Greenland ice sheet in the northern hemisphere, which has about 7.4 meters sea level equivalent. And all the rest of the ice in the world, all the glaciers in the world, which are all these yellow ones on this figure, they have a sea level equivalent of about 0.4 meters. So in terms of the threat to sea level rise, glaciers are a smaller volume of ice than places like Antarctica. But because they are small, they can respond rapidly, and so we may see substantial sea level rise from glaciers over the next few decades to centuries. If we go back to around 27,000 years ago, sea levels were 130 meters lower than today. So in addition to the Antarctic Ice Sheet and the Greenland Ice Sheet, there was a large ice sheet over North America called the Laurentide Ice Sheet, and a large ice sheet over Eurasia called the Eurasian Ice Sheet or the Scandinavian Ice Sheet, and we had a growth of glaciers in alpine regions across the world. And all that ice made sea level about 130 meters below present. So if you go to the beach today and you dip your toes in the sea, you're paddling about in ancient ice sheet. If you just think about what this means, during the last glacier maximum, which was about 27,000 years ago, you could walk from Britain across a land bridge into France. And you could, there's mammoths roaming around on the steppe plain in front of the ice sheet margin. So a very, very different world. Let's put this in context to carbon dioxide. This is carbon dioxide over the last 800,000 years, and it's carbon dioxide from ice core records. And during that last glacial maximum, which was about here, global carbon dioxide was 185 parts per million. The pre-industrial carbon dioxide, so pre-1800s carbon dioxide, was 280 parts per million. So an increase of about 100 parts per million of carbon dioxide was enough to melt all those ice sheets and raise global sea levels by 130 meters. In 1958, carbon dioxide was 315 parts per million, and in 2019, we reached 411 parts per million. This is now substantially higher than anything we've seen in the Quaternary period, so anything in the last 2.6 million years, and we have to go further back into the Neogene to get carbon dioxide levels of this kind. So there's a critical question. If carbon dioxide increases around 100 parts per million resulted in the ice sheets disappearing, then what will happen when carbon dioxide increases as much as it has today? How will today's ice masses respond to this massive increase in carbon dioxide and the concomitant increases in temperature that we are committed to? First of all, in order to answer these questions, we have to understand how ice masses behave. We have to understand how they've responded to past climate change, and we have to be able to use numerical models to project future change of these glaciers. These numerical models will improve projections of future sea level rise, water shortages, droughts, and floods. How do we know which numerical models are right? How do we have confidence in numerical models? And the way in which we do this is we test these numerical models against the past record of glacier change. We can run many simulations, and the simulations that can best predict glacier behavior under a variety of different climate states can be useful for projecting future change. Let's now move to Patagonia. Patagonia in southernmost South America is currently experiencing substantial glacier loss. Across South America, it's losing 19 billion tons, a gigaton is a billion tons of ice. Most of this is from southernmost South America, and is contributing around 0.5 millimeter per year to sea level rise. This doesn't seem like a lot for sea level rise, but it has real implications for water resource management, for hazards, and for glaciers and the relationship between glaciers and climate. If we put this in a global context, we can see that the Southern Andes, which are here, this big red circle, the Southern Andes, have lost 1,208 gigatons of ice since 1961, and about 360 gigatons will contribute to a global sea level rise of 1 millimeter. And actually, the Southern Andes have contributed, they're the third largest contribution to global sea level rise in the world. So Alaskan glaciers and the Greenland glaciers are contributing the most. This is contribution from glaciers, so it's excluding the Greenland ice sheet and the Antarctic ice sheet. So after Alaska and the Greenland glaciers, these Southern Andes are contributing the most, and they have one of the severest negative mass balances in the world. So that means that they are losing far more ice than they gain each year. These glaciers in the Southern Andes are important for the local community. So in this piece of work, we looked at the supply of water from glaciers, and we looked at the demand of water. And in the Southern Andes, there is a high demand on the water in these glaciers. So people are very keen to receive the water from these Patagonian ice fields. And these Patagonian ice fields are very vulnerable to changes in precipitation, which are projected to change. They're also very vulnerable to increases in population and increase in GDP, which will increase the demand on the water from these glaciers. So increasing demand, decreasing water is likely to be a problem in southernmost South America in the future. And indeed, it seems that these glaciers surrounding the Patagonian ice fields, these glaciers have already reached what we would call peak water. So peak water is the period of time when the most water is being delivered to the downstream catchments. As the glaciers get smaller, as they shrink, there's less volume, there's less melting, and so they produce less meltwater to the downstream catchments. And the catchments around the Patagonian ice fields reached peak water sometime in the last 20 years, so between the year 2000 and the year 2015 for the different catchments. This means that due to increased projections of demand and decreased projections of glacier shrinkage, we're likely to see increasing water stress in Patagonia. So we know that the glaciers are shrinking, and we know that this is going to be important not only in terms of sea level rise, but in terms of society's dependence on water. But how unusual are these changes in the longer term context, and how will these ice fields behave in the future? One thing that we still don't really understand and that we've been arguing about in the academic literature is what are the drivers of glacier change and what are the mass balance sensitivities? Patagonia is quite complicated. The glaciers carve into lakes and they carve into the ocean. And they may be responding to northern hemisphere type climate signals like the Little Ice Age and the Younger Dryas, or they may be responding to southern hemisphere Antarctic type climate signals like the Antarctic cold reversal. So the climatic and the glaciological controls, such as the rate of carving, the depth of the lake, are difficult to untangle. We therefore need empirical reconstructions, so data-led reconstructions of past ice sheet dynamics. This will help contextualize current change, and it can be used as a robust data set to calibrate numerical models. And it allows us to generate a target for numerical models so that we can evaluate what the most important controls are. And ultimately, large empirical data sets can shed insights into these paleoclimatic controls on ice versus the internal controls on ice dynamics, which could be things like topography and water depth. It allows us to improve our understanding of the controls on the past, the present, and critically the future of ice dynamics. And it helps us to understand the role of things like the Southern Westerly Winds, the Southern Annular Mode, and El Nino, and other modes of climate variability in controlling these ice masses. So the PATICE project aims to compile published ages and geomorphology from 38 to 56 degrees south, so from the Chilean Lake District right down to southernmost South America. These ages have all been put into a GIS, and they've all been recalibrated and recalculated and assessed for reliability. The ages and the geomorphology together allow us to reconstruct the ice sheet and the paleo lakes. And for the first time, we attempt to do this at 5,000 year intervals. So not just for the last glacier maximum, but from the last glacier maximum right through to the present day. And it allows us to highlight the future research priorities and the gaps in our knowledge. So this is Patagonia. This is our study area. This is 38 to 56 degrees south. Most of the glaciers here are aligned north to south along this Andean mountain chain, and their flow is orthogonal down the mountain slope. So most glaciers flow east to west with an ice divide along that mountain chain. Mountains in this area are not so high, they're about 4,000 meters high, and they support 4 key ice fields. There's the Northern Patagonian Ice Field, or the NPI, the Southern Patagonian Ice Field, or sometimes abbreviated as the SPI. There's Gran Campo, Nevada, and Cordillera Darwin in the southernmost South America. Together, they cover 27,000 kilometers squared, but in places, the glaciers are very, very thick. And so they have a total glacier volume of 5,500 gigatons of ice, which would be a sea level equivalent of 15 millimeters. So if you remember in context, the global glaciers have a sea level equivalent of about 41 centimeters. They're a unique natural laboratory because they are extending, these glaciers extend over a very large latitudinal transect. And they are ideally located to be capturing precipitation delivered by the southern westerly winds. The southern westerly winds are these winds which flow around the Antarctic continent. And these southern westerly winds bring substantial precipitation. So in the first panel here, panel A, we have temperature. So we have the temperature change. You can see the glaciers coming out as very cold. And it's nice and warm up here in the north. But then in panel B, we have precipitation. And Patagonia has one of the world's most steep precipitation gradients from west to east. So we get large amounts of precipitation on the western coast and limited precipitation across Argentina. And this is what's contributing to this water stress. And then in panel C, we have wind speed. And you can see we have the subantarctic front, which is just to the south of Patagonia, and the subtropical front just to the north of Patagonia. And the southern westerly winds are flowing around the Antarctic continent within that belt. Because they bring so much precipitation, as the core belt of these westerly winds changes, the glaciers receive dramatically different volumes of precipitation. So as the southern westerly winds contract more towards the South Pole, it's drier in Patagonia, and the glaciers therefore shrink and recede. If the southern tropical front expands northwards and the westerly winds are able to expand northwards, then the westerly winds cover more of Patagonia and the glaciers receive more precipitation. So we know that in the last glacier maximum, the core of the westerly wind belt was further north and the glaciers were receiving plenty of precipitation and therefore were able to sustain very large ice fields. And then today we have the situation with very contracted southern westerly winds. And Patagonian glaciers are thinning and receding. The north and south movement of the southern westerly winds is controlled by the Southern Annular Mode. So this is the pressure difference across a gradient, a latitudinal gradient. And when you have a positive Southern Annular Mode, a positive SAM index, the westerlies are weaker over Patagonia, it's warm and dry in Patagonia, and glaciers recede. And incidentally, when you have a positive SAM and these contracted westerlies, you get a lot of glacier recession in Western Antarctica because of the effect of these winds on ocean circulation. So you get, in a positive SAM index, you get glacier recession in Antarctica and glacier recession in Patagonia. If you have a negative SAM, the westerlies expand northwards and you get stronger winds and more storms over Patagonia. It's cold and wet and the glaciers love it. They all get much bigger. So as the SAM flips on a sort of century scale or decadal scale, you get positive and negative SAM, the westerlies are contracting and weakening. So I think this really highlights the importance of that latitudinal gradient. Because you have this long latitudinal gradient of glaciers that are very sensitive to the winds and sensitive to the Southern Annular Mode, you can start to use the glaciers as a proxy to understand the past change in the Southern Annular Mode. And that's critically important because these changes in these winds are strongly affecting Antarctica today. We also can reconstruct past SAM behavior from paleolate records, pollen records, lake levels, things like this. So we have a number of independent records of precipitation and wind strength. El Nino also affects Patagonia. So in this figure here, you can see the amount of precipitation received across the southern Patagonian ice field, and the very strong El Nino year in 2016 resulted in severe drought in Patagonia, much drier conditions, and significantly weaker precipitation across Patagonia. And El Nino events are forecast to increase in frequency over the 21st century. So this is the year 2000, this is the year 2050, and the extreme El Nino events are forecast to increase substantially. So those are the main climatic factors affecting Patagonia. Let's think about Patagonia during the last glaciation. Patagonia was originally mapped by Cordenius in 1932, and he mapped the entire length of the Patagonian ice sheet by horseback, a phenomenal effort with very, very detailed geomorphological maps produced across the entire length of Patagonia. An absolutely outstanding piece of work published in 1932. And actually, the reconstruction that he produced has little changed since then. Cordenius did not have access to any dating methods, so he used a relative chronology, assuming that the oldest, the outermost, most degraded moraines were oldest and the freshest moraines were youngest. Since then, our understanding of the Patagonian ice field has remained largely the same. A large ice sheet that centered along the Andean mountain chain with an ice flow north to south, orientated north to south along this mountain chain, the glaciers flowing out east and west with large outlet lobes occupying these topographic lows. So large outlet lobes going up and down this coastline. The western coast, very difficult to access, mostly at the continental shelf. And there have been hundreds of ages now published on the Patagonian ice fields. Radiocarbon ages, cosmogenic ages, tree rings, lichens, lots and lots of different approaches have been applied. But to date, there has not been a systematic attempt to compile all of these ages into a database, no systematic reconstruction of the paleolakes, and no systematic reconstruction of the recession of the whole ice sheet. The paleolakes are really, really important. Here is just an example from the northern Patagonian ice field, and we have two large lakes, Lago General Carrera, Buenos Aires, depending on whether you're in Chile or Patagonia, Chile or Argentina, and Lago Cochrane Pueyrredon. And I do apologize for anyone who speaks Spanish for my appalling pronunciation. It's on the list of things to do. These two lakes currently drain out through the Rio Baker into the Pacific. So they drain out south of the Patagonian ice field, the northern Patagonian ice field, out into the Chilean Lake District. But you can see immediately from the LGM reconstruction that the last glacier maximum would have impeded that drainage. And so during glacier recession, the ice was unable to drain out through the Rio Baker, and so it drained out across Argentina through Rio de Janeiro. So there was a number of drainage reversals during deglaciation. As the Patagonian ice field started to fragment, these paleolakes changed in lake level. The lake level dropped and would occasionally catastrophically drain. And we know that the drainage events would have been catastrophic because they left behind the geomorphic scars on the landscape, scattered large boulders attesting to the volume of water that poured out of these lakes. So as your ice sheet is carving into a lake and that lake suddenly drains, that is going to have a significant impact on your ice dynamics. So the changing lake levels and the relation of these lake levels to the ice dams and the coals and the impact of the lakes on the glacier extent is a significant complicating factor when we try and understand the past ice sheet dynamics in this area. It's also important because suddenly dumping a lot of fresh water into the Pacific Ocean could well have infected regional climate, and that could have affected again the ice fields. So some nice modelling work by Neil Glacier shows that dumping, and Joyce Araya shows that dumping fresh water into the Pacific Ocean could have affected the Patagonian climate. Okay, so I want to now go through some of the methods that we've used in trying to reconstruct the Patagonian ice field and the paleo lakes. Firstly, the input data is the chronostratigraphy, so it's various ages that show us when ice-free conditions were existing, and ages that show us when the glacier lakes were in extent and when the glacier lakes drained. So we're looking for ages that tell us that we have ice-free conditions. And I gleaned all of these from published data. Then we have our published geomorphology, things like moraines or paleo lake shorelines, deltas and river terraces and lake terraces, cirques, things like drumlins and flutes, meltwater channels, coals and spillways, all sorts of things. And then we have high resolution satellite imagery from various sources, the GEBCO 2019 bathymetry from the offshore area, and the ASTG-DEM. These data were all put into a database. So ages were published, were plotted into a GIS. I found quite a few errors in publications whilst I was doing this, and so they were all corrected. And the ages were recalculated or recalibrated where appropriate. They were then subject to quality control or reliability rating. So doing things like excluding outliers, excluding ages that were missing date, like a context that enabled me to understand what they were actually dating. And because our protocols for dating glacial environments have improved over the last 50 years, this means that older ages tend to be viewed as less reliable than ages that have been published more recently that have better protocols and methods. The geomorphology was compiled and plotted in a GIS, and we also did an amount of new mapping in data poor areas. So areas that were lacking in mapping, that were blank, we tried to infill that using our remotely sensed data sets. And this enabled us to understand when land was glaciated or ice-free, areas that may never have received ice. So here's just an example of a nice moraine, and you can see the flat-topped delta terrace in the background and the beautiful Baker Valley. We then moved to the glaciological reconstruction. This was very much the hardest part of the exercise. Well-dated moraines are straightforward. So where we have moraines with good ages on them, we are able to create an isochrone of that moraine. So we know that the ice was here at this time. We then attempted to interpolate between isochrones at these 5,000 year time slices. So we attempted to say, well, I've got two isochrones here at 19,000, so I'll draw my 20,000 year ice margin in this area. We used the topography a lot to assist with this. We know that the geomorphology is very much focused on the valleys, and there are trim lines and things. So you can use the geomorphology and the topography to construct the ice margin. And we were trying to determine the location of the ice dams and the paleolake extent at each time. So relating the height of the lake to a specific geomorphic point or spillway that would have been blocked by an ice dam, and trying to work out the relationship between the two. We have an uncertainty estimate and ice sheet extent. So places where we're highly confident in the ice extent, medium confident and low confident. And the areas that are low confident are lacking geomorphology and they're lacking ages. And in these low confidence areas, I would say that the ice extent is a hypothesis that we would invite people to go and test. And you could use perhaps this to guide your fieldwork. We use the topography to calculate the ice flow in the ice divides at the last glacier maximum and calculate glacier area. And then we calculated the volume of the ice using volume area scaling, nothing more complicated than that, with different scaling laws depending on whether you were looking at an ice sheet or a glacier or an ice dome. And then we produced the database and the reconstruction of supplementary data, which is available to download from Mendeley data, and it's linked from the publication online. So this is the database. We divided our ice field up into these 6 sectors, and we'll go through them one at a time. The database includes 58, nearly 59,000 landforms, and we were using these landforms to understand the land systems, the glacial land systems, the types and styles of glaciation. So we have many moraines, lineations, empty cirques, glaciers, trimlines, perch deltas, all sorts of things. And you can see them all mapped in this figure. So we have the moraines are in brown, the deltas are in yellow. They're a bit hard to see at this scale. So we move to the chronology. There are many methods for dating glacial landforms. Each method is applicable to a certain set of environments or circumstances and over a certain time range. So historical archives may go back 200 or 300 years. Lyconometry may go back several decades to a couple of hundred years, maybe 500 years. And then in longer term, we might be able to use tephrochronology, which is ash, which may be interbedded within moraines or in peat bogs between moraines. Varve years are the annually laminated lake sediments, and we can count the number of years because each layer is 1 year. Dendrochronology, cosmogenic nuclear dating. Cosmogenic nuclear dating is the dating of glacially transported boulders on moraines, and that's been very widely applied in Patagonia. And radiocarbon dating obviously has long been a very popular method of dating techniques. In case anyone's not familiar with cosmogenic nuclear dating, I think most people have a working understanding of radiocarbon, but in case anyone's not familiar with cosmogenic nuclear dating, this assumes that in a glacial environment, if you're trying to date boulders on a moraine, that your boulder will have been plucked from the cliff face and transported by your glacier. This boulder is shielded by anything covering it from cosmogenic rays. So a depth of water or a thickness of ice or a thickness of rock over it will attenuate the cosmogenic influx and prevent the boulder from receiving it. Once the glacier recedes and the boulder is left behind on the moraine, the atoms in the quartz in the boulder are able to interact with the cosmogenic rays. And these cosmogenic rays cause a new cosmogenic nuclide to be formed in the boulder. So the most common cosmogenic nuclide that we use is beryllium-10 because it forms really nicely in quartz. We do use other ones, but 10Be is the most common. And so the hypothetical ideal case would be your boulder has no 10Be because it's been shielded, the glacier transports it, the glacier retreats and it starts to accumulate 10Be, and as the boulder is exposed over thousands of years, the 10 beryllium concentration increases. Sadly, this ideal case is rarely the case, and a large number of factors can interfere with this. For example, your boulder could have an inheritance. Your boulder could have 10Be from previous exposure, and then you get an anomalously old age. It overestimates the deglaciating age. Or perhaps your boulder will roll or topple or be buried and then exhumed, and that will give you an anomalously young age. So if we plot the probability to density function of different ages, you may well get quite a lot of scatter. And so here you could say that perhaps this blue age is an outlier because it's forming a double peak in our probability, our summed Gaussian probability density function. So when you're looking at cosmogenic ages and all other ages, there is a need for outlier detection and this ranking of ages in order to not treat all ages the same. Each age needs to be very carefully considered within its own range of circumstances and ranked according to whether or not it was an outlier, whether or not the age was done according to reasonable protocols. So these are our ages, a large number of radiocarbon ages, around 600 cosmogenic nuclide ages, and then smaller numbers of a wide number of other ages. And here you can see in the figure, the triangles are the cosmogenic nuclide ages and the red stars are the radiocarbon ages. So you can see that they are focusing on key outlet lobes. So some outlet lobes are substantially more targeted for radiocarbon, other outlet lobes, cosmogenic nuclide dating is more appropriate. And it very much depends on whether you have organic material to date within your moraines for radiocarbon, or whether you have boulders to date, or whether you can find any volcanic ash around that you can date. And that's why there's a spatial disparity. The database of all of these ages is available on Mendeley, and it includes unique attribute fields for each age, which include a unique ID, a reference, a landform description, a context description, and all the data needed to recalculate the age. So for cosmogenics, that's sample thickness, shielding, latitude, longitude, elevation, things like this. The standards used, the erosion rate, the rock density. The tephra includes attribute information on the tephra source, the layer, the tephra age. The radiocarbon, if it's offshore, includes the marine reservoir used, the delta R, the uncalibrated ages and the uncalibrated error, as well as things like latitude and longitude, and also includes the delta 13 and the material dated. So the ages are all given a reliability assessment, so that you can see that a large number of radiocarbon ages are rated as amber rather than green. This is largely because a lot of these radiocarbon ages are from sort of older publications, and it can be sometimes difficult to understand the context, or there is incomplete information provided. And then we have some ages that are red. Often these ages are those that are identified as outliers in the original publications, and so they're included, or they fail our quality control in some way. And then we have a number of other ages. As 10 BE ages are those generally most appropriate for calculating the mean age of a landform. We use these to calculate average landform age. So we only do this on beryllium 10 ages on moraines, where we have a number of moraines, a number of boulders on one moraine, and we can exclude any outliers. So we only use the green ages. We give the standard deviation, which gives an assessment of the spread of ages across that landform, across that moraine. So this is how we reconstruct the ice field. So we start with our GIS database. In panel A, you can see the geomorphology. We have the moraines. In pink here, you can see some drumlins or some flutes. The speckled yellow, you can see this, the fluvial outwash terrace. Then in dark red, we have some little cirques and things like this. And this black with a white outline, that's the glaciers today. Then we have all these ages. The star is the radiocarbon, for example. The green is the cosmogenic nuclide. And you can see the circles around the ages. And those circles are the reliability assessment. And the pink numbers are the average landform ages, the mean ages, with the standard deviation in brackets. We then, in panel B, reconstruct the ice margin. So you can see up here, around Paleo Lake Tar, we have a green outline. This is because for this time slice, we have a high confidence in the ice margin because we have some good ages and some good geomorphology. In panel, this outlet lobe just down here, you can see that we have an orange margin. This is because it's well constrained geomorphologically, but as you can see, there are no published ages for this moraine. And the same for down here, no published ages. And then in between, we have a red outline. This is because we're lacking any geomorphology and we're lacking moraines. So this is our best estimate of where the ice margin would have been. We know that it would have been in here because we have evidence of glaciation, but we also think these fields, these mountains were remaining ice-free because they mainly have a fluvial geomorphology rather than a glacial geomorphology. And then finally, in panel C, you have the flow lines put on. So these are showing the direction of ice flow. And this is because we can make assumptions about whether we're looking at terminal moraines or lateral moraines and the topography about the direction of ice flow. Let's look a little bit about what this compilation of landforms tells us about the style and manner of glaciation. we can identify 4 key land systems. The first is a mountain glacier land system. This is very active in Patagonia today. Then we have a lowland land-terminating glacier. So this is a large lobe of ice that's terminating in a dry environment. Lowland glacial lacustrine, so a glacier that's terminating in a lake, and glacier marine. So I'll go through them one by one. This is the upland alpine style glaciation, still very present in Patagonia today. You can see these beautiful examples of flutes here with little sawtooth moraines. This is from Julian Martin's work. Little sawtooth moraines here coming up here. And you can see a nice photograph here of the example of that land system. Lateral and frontal moraines, an active temperate glacial land system with active mountain glaciers. The lowland land-terminating land system, here's an example from the terminal environment of Lago Buenos Aires. And you can see these substantial moraines, substantial nested moraines. The grey is the moraine complex and the black is the moraine ridge with meltwater channels in between. So the meltwater channels tell us we're in a subaerial environment. And then within the moraines, we have the green lines, and these are the shorelines. So you can see that in this particular case, we had a land-terminating glacier, and as it receded, it evolved into a lacustrine terminating glacier, terminating in a lake. So we have lots of evidence of outwash, subaerial outwash. We have moraines and meltwater channels. There's an outwash plain here. Paleofloods are shown here, alluvial fans, bedrock channel, paleo channels and bedrock lineations are also very common. And then Patagonia is really overprinted by this glacial lacustrine land system. So here's also an example from Lago Buenos Aires or Lago General Carrera. Here is the lake. Here is the alluvial fan that's forming today. Here's your little river flowing down, it's making this little delta here. And then above it is the perch delta. And that perch delta formed at a higher lake level. So the perch delta, the flat top of that, gives you the height of the paleo lake. And you can align these paleo lake deltas along the length of this paleo lake. And they occur at a number of different elevations. There is an added complexity because the lake is so long and so large that there's an isostatic difference between the east and the west. So they don't necessarily line up, which has made it extremely challenging to identify the location of the coal. But I think we have an estimate now. I'm sure it will be revised in coming years. So we use these geomorphological features together with a chronology to try and work out where the coal was and where the ice dam was. So we have here some examples of some perch deltas. You can see that this would have been an area with, here's your lake today, here's your delta today, and you've got your higher deltas. You can see the lake would have been at this level in the past. Here are some nice examples of shorelines around the same lake, and you can see the raised deltas in this photograph here. They are strongly evident all the way around the lake, like a bathtub rim. Unfortunately, they don't always line up, but they give us very clear evidence of rapidly punctuated drainage, with the lake falling and draining very rapidly. And this glacial lacustrine land system is associated with these glacial lacustrine sediments. These are laminated lake sediments. Typically they are varved, which means they have a winter layer and a summer layer that form every year. And often they have drop stones in them. These are stones that have been rafted in by icebergs and have floated around and fallen in. So we can count the layers within these varves, and they tell us how long the lake was in existence. And one thing that has worked really, really well is linking these varves to the tephra, the volcanic ash. So there's volcanic ash layers within these glacial lacustrine varves. And if you look at some of Jacob Bendel's work, he's been able to link the varves to the tephra to get a very precise anchored chronology that tells us the exact years that the lake was in existence with very tight error uncertainty margins. And then he's able to link that to the moraines. So we get a varve age for the moraines and compare that to the 10BE age of the moraines and really tighten our chronology. And this is just a nice example of a hillside with a shoreline wrapping all the way around it. This is telling us about a small lake, a large lake that was in existence at 350 meters above sea level. You can see there's no lake there anywhere near that elevation now. And then we used the GEBCO data set together with some high resolution geomorphology that's been published over the last few years with Julian Dowd as well. So we have the GEBCO is fairly low resolution visualization of the continental shelf. But we have these areas with very high resolution geophysical surveys. The GEBCO database does reveal that the continental shelf is characterized by these deep bathymetric troughs. And they're very similar in their dimensions and their shape and their configuration to the bathymetric troughs we see surrounding things like South Georgia on the South Georgia continental shelf. So I would say that these were likely to be formed by ice streams or very large glaciers during the last glacier maximum that were extending out to the continental shelf edge. And it would be very exciting to look at these with higher resolution spot bathymetry to see if we can see things like moraines or whether it has been removed by vigorous coastal current action. But I think we have sufficient evidence to say that these continental shelf cross bathymetric troughs across the continental shelf are characteristic of ice streams that have been observed in other areas. Okay, I want to walk you through the reconstructions that our database has allowed. We'll start with the Chilean Lake District. The Chilean Lake District has very small, very minor glaciers now. They're on the top of a few small volcanoes. You can see them in bright blue here in turquoise. And during the last glacier maximum, there was a large expansion of ice here that expanded out to fill these over-deepenings to form these piedmont lobes. So we have these really nice piedmont lobes. And they're extremely well dated with radiocarbon dating. There's a very nice chronology here with organic material interbedded within glacial diamicton. And that's enabled a strong chronology to be developed. So we have high confidence on this side, but this side is extremely poorly studied and there is very little data here at all. So if anybody is interested in a trip to Patagonia, then these sites here would be well worth going to. There's very little chronology there. The pulling back of the ice occurred around 20,000. So the ice reached its maximum extent around 35,000, and by 20,000 was starting to recede. Ice extent at 15,000 is very poorly known. We do know that a paleolake developed here. It was one of the earliest paleolakes to be mapped in Patagonia. So we know that there was a paleolake here. So we know that there was ice persisting long enough to form the paleolake, but the chronology is very poor. From the Antarctic cold reversal around 13,000, again, ice extent is very poorly known. And ice extent in the Holocene is really poorly known. So this would be a really interesting area to target for future studies because the Holocene ice dynamics are well known further south, and understanding those teleconnections to further north would be scientifically very exciting. Just south of the Chilean Lake District, in this sector, we have more information from the eastern side. So we have some nice chronologies and nice mapping here, and we know that we have a number of lakes that started to develop. Again, it's quite well constrained at the last glacier maximum, reaching that around 35,000 years ago, with recession initiating probably around 20,000 years ago. But again, we're lacking dating control on this. Around 13 Ka, we have a very large lake being developed. There's some nice geomorphological evidence of this, which does indicate that the ice persisted long enough to develop the lake. And then during the Holocene, again, very poor chronology and geomorphology available to understand ice behavior at this time. The northern Patagonian ice field is probably one of the most intensively studied areas. So we have quite high confidence in ice dynamics in this area. And one of the real advances in science over the last couple of years has been understanding the really complex behavior of the lakes. We know that the glacier was around its maximum extent probably before 35,000 years ago. And by 30,000, it's still there. And by 20,000, 25,000, it's already started to recede. So the glaciers are achieving their maximum extent before the global last glacier maximum. And then they remain fairly stable through the global last glacier maximum. By 20,000, they're starting to recede with increasingly rapid recession after about 18,000 years ago. And that's probably controlled partly by rapid warming, but also partly because of the development of these very, very large lakes. So you can see between 20,000 and 15,000, we lose a large amount of ice, with these lakes developing very rapidly and precipitating very rapid calving. We find the coal here for the 420 meter lake. So we know that this ice dam had failed and allowed the development of the 420 meter lake around 15,000 years ago. And by 13,000 years ago, the lake had dropped to 350 meters, which means that the Bayo coal, which was first identified by Glacier et al., is coming through in this way. And I think Farrell Thornycroft's paper in QSR 2019 was quite important for unraveling this really complicated relationship between the glaciers and the lakes. So by 10,000 years ago, we think the lakes have pretty much reached their current extent and current drainage configuration, with some nicely well-dated re-advances during the mid-Holocene and the late Holocene. So we know that these glaciers were advancing around 4,000 to 6,000 years ago, and around 1,000 to 2,000 years ago, and in the last couple of hundred years. Southern Patagonian ice field, again, some outlet lobes here are very, very well dated, allowing us to have quite high confidence, particularly for certain time periods. So we have some nice big ice streams coming off here. This ice flow constrained by the bathymetric troughs on the cross shelf. Some nice paleolakes starting to develop here. And then again, some really complicated dynamics between the glaciers and the lakes that were quite challenging to unpin, with the glaciers and the lakes co-evolving together. But we have a model here for Paleolake Teleche at 250 meters, was the coal here, which then merged with another lake to form the combined Paleolake Teleche Puerto Consuelo Lake, which by 10,000 years ago has drained, and the lakes are pretty much at their present day configuration. And in parts of Patagonia, you can see these flashes of green. We have very, very well constrained re-advances around 4,000 to 6,000 years ago, again around 1,000 to 2,000 years ago, and again in the last few hundred years. So we know that these glaciers are behaving with these advances during the Holocene. Then in Gran Campo, Nevada, again we have the very large ice reaching its maximum extent probably well before 35,000 years ago, with the glaciers receding, complicated lakes. We know that there was a lake here, but we think it's drained by 15,000. So unfortunately, it doesn't make it into our time slice. It was probably here between 20 and 18 or something. And then by 10,000, again, these ice dams are removed and the lakes have turned into the tidal fjords that they are today. And then the final part, in the southernmost part, you can see again big ice streams extending right out onto the continental shelf on the other side. And then by 5,000 years ago, they are largely at their current extent, with some nicely well-dated mid-Holocene advances. We can plot all of these ages. These are all the beryllium ages into various things, and I'm running short on time, so I will be brief, but you can see the histogram here showing clusters of ages during the Antarctic cold reversal, mid-Holocene, the late Holocene, and Little Ice Age. And then this box plots show each box is a moraine, and you can see that the southernmost lobes of the Southern Patagonian ice field are reaching their maximum extent around 47,000 years ago. And then remaining stable near that limit around 30,000 years ago, and still near the limit around 20,000 years ago. So these moraines the glaciers are reaching that maximum extent well before the global ice maximum in MIS3, and then pulling back. So the last glacial maximum was around 33 to 30,000 in the north, and 47 to 30,000 in the south. the smaller extent during the global LGM from 19 to 23,000 years ago. So still fairly large, but pulled back slightly from that maximum extent. So by 25,000 years, we have a small recession, and then by 20,000, we're already well underway with deglaciation. And again, that occurred earlier in the north than in the south. By 15,000 years ago, there is widespread evidence of paleolakes. We know that the glaciers are stable through the Antarctic cold reversal. There is a large number of moraines, well dated, showing stabilization of the glaciers during the Antarctic cold reversal, although little indication of this further north, I think probably due to a lack of data on this. 13,000, we're just at the end of the Antarctic cold reversal. You can see the evolution of the lakes. During the early Holocene, a minor stabilization, synchronous with the Younger Dryas in the Northern Hemisphere around 11,000 years ago, and the paleolakes have largely drained. Neoglaciations in the Holocene, 5,000 years ago, 1 to 2,000 years ago, and neoglaciations north of the Northern Patagonian ice field, not well constrained, and a widespread advance in the latest Holocene. PATICE is about 12% larger than the last reconstruction by Coronado and Rabassa, and we calculate a sea level equivalent of about 1.5 meters. And this makes an ice sheet similar in size to the Antarctic Peninsula Ice Sheet today, so to give you some idea of scale. So this is just a nice image showing our paleolakes and ice sheet reconstruction with the change in sea level and the uncertainty margin. Glacier lake area reached a maximum around 30,000 years ago, but is now increasing as glacier lakes are shrinking. And I just wanted to highlight that glacier recession reached its peak during the post-LGM period around 20 to 15,000 years ago, but the current rates of recession rival this. For a glacier, for ice sheet that is an order of magnitude smaller and does not have the rapid changes in glacier lakes that were identified previously. We note that the local LGM was driven by Southern Ocean surface temperatures, and then deglaciation probably driven by rising global sea levels. The Antarctic reversal around 14 to 12,000 years ago, and then smaller readvances at 11,000 years ago.
Dr. Davies, we will need to.
Yeah, I'm sorry, I'm overrunning. We can just say that this is influenced strongly by the Southern Annular Mode, and we can take any. We'll stop there, and we can take any questions from there from now on.
So we are just at time. We usually wrap up at this hour, but if there are any questions from the audience that anybody would like to pose, please do send them forward now. I suppose as a general question, since before we wrap up, you know, there's such an intricate investment of manpower, effort, and labor hours into reconstructing the time change overall. Where do you see this in contributing to broader policy debates around climate change and bringing forth this kind of evidence?
In terms of policies, I think one of the key things that we can note is that the rates of recession that we see today are unprecedented. We see very rapid recession over the last few decades, and it's rivaling the very, very rapid recession we see during that last glacial interglacial transition, and it's faster than anything we have records for over the Holocene. So we know that the glaciers are receding really, really rapidly, and I think we can begin to say that they're receding more rapidly now than we have done before. These are the kinds of statements that are simple and easy to make, but having the data to back them up can often be very, very challenging. So being able to say that the glacier recession we see today is unprecedented and is different to the norm and is different to what we've said before and what we've seen before, and is not just a continuation of a longer term response to climate change is very important.
Well, thank you very much for the painstaking work that you and your team and the wider community are doing to to bring forth this very critical and crucial evidence. I hope that our scientific community and those of us in the audience today, that we do try to get more of this into the public realm. At least that's the hope with this series. And so I thank you on behalf of all of us today. And for those of you who are still tuned in, please make sure to follow us on Twitter at UMCrisisStudies. Next week, we'll be talking about disaster resilient flooding and infrastructure in Egypt and Thailand with Dr. Ruwaida Al-Hamad. And so thank you all for tuning in this week. Oh, we have a last question. Sorry. Oh, right. Okay. So this talk by Dr. Davies will be posted on YouTube. So if you want to review any of the wonderful data publications that she's mentioned and cited, it'll be on YouTube in the next few days. Thank you very much, Dr. Davies, for being with us this week.
Thank you.